And I'm also very glad that Alicia actually introduced the whole field of gamma rays like this. I can actually go quite quick on the part that I'm going to speak about gamma rays. So today I'm going to be talking about dark matter in the multi-messenger era. So this is a topic that I've been working for quite some time. So this is basically the outline of my presentation. So basically, when we're talking about multi-messenger, we are talking about what we call indirect detection of dark matter. So I'm gonna describe a little bit what is the main idea, the basic principles of indirect detection of dark matter, or indirect searches of dark matter. Then I'm gonna go through some of the different messengers that we can use to detect dark matter indirectly. I'm going to talk about gamma rays, a little bit about neutrinos. Then I'm going to talk about cosmic rays. Yeah, I'm going to end with cosmic rays. So just a small disclaimer, this is a very large topic. There is actually even more indirect detection stuff that we can talk about that I will not have time to talk. There is dark matter in extreme environments, close to mergers and things like that, which is a very new thing that people are developing. I'm not going to have time to talk about that. So this is a very personal selection of recent results. I'm going to describe a little bit the general aspects of indirect detection of dark matter and then go through some of the most recent results. This is a very short talk. It's not a full lecture. I'm going to go and give you a basic overview of where we are in this type of searches. So to begin with, for this talk, we have basically two hypotheses. One is that dark matter does exist, okay? We know that most of the gravitational mass of galaxies and galaxy cluster is actually comprised of dark matter, of invisible matter. We can see that this matter is most likely distributed in large halos around the galaxies. This we can see very clearly with these rotation curves that were observed in the beginning by Vera Rubin back in 1980. They are practically non-collisional. This we can also see from the collisions of clusters where we can see the detachment of what we call the gravitational mass, which is basically seen with the gravitational lenses in radio, and the gas, so the visible mass, actually they get detached. So because dark matter actually crosses without collision, and matter, actually you have this collision between the matter. So they get detached. And also this dark matter will be non-baryonic. This actually comes from cosmology. That's one of the places where we have this very strong evidence that dark matter is a particle, okay? Now, all these evidences of dark matter, they come from astrophysics. So that's why also we think that looking into astrophysics is actually one of the best places to look for detecting the dark matter particle. Now, the second hypothesis is that dark matter is this particle and it decouples non-gravitationally to the standard model particles. So the main processes that we're going to be looking for are either what we call annihilation or decay of these massive particles. They will produce massive standard model particles. These will decay, hadronize decay, and they will produce gamma rays. And at the final state, they will produce stable particles that will be detecting. Now, let me tell you a little bit about what we call the WIMP miracle, or what is understood as the analysis of the relic density for a hypothetical new particle. So there is this scenario that we typically start when we talk about dark matter for undergrads or school, where we show that pi, where we have 70% of dark energy, 26% of dark matter, and basically 5% of all the rest. So this actually comes from very detailed surveys and observations where we can actually constrain all these parameters. And normally, in order to constrain these parameters, we have to assume a cosmological model, and the cosmological model that we mostly use nowadays is the lambda CDM. So in this model, we can actually make a very simplistic hypothesis where you assume that you have a new particle, and this particle will couple with the standard model particle, and it will be in the thermal bath in the beginning of the universe. So the equation that drives the interaction between dark matter and the standard model is what we call the Boltzmann equation in comoving volume. This is a very simple equation. And here you can actually see this equation happening. This is the term that depends on the expansion of the universe. And what happens is that at a certain point, because of the expansion of the universe, of the cooling of the universe, this reaction will not take place anymore, and you're gonna actually, everything that's gonna be annihilated will not go back into dark matter. So at a certain point, what will happen is that we're gonna have a freeze out. That's what we call a freeze out. Basically, and this freeze out will depend on this parameter here that is called the cross section, the annihilation cross section. Now, if this annihilation cross section is and basically also depending on where this freeze out happens in the evolution of the universe, you're going to actually have a density of dark matter that will be actually fixed. So in this very simple scenario, if you have a very small cross section, you're going to have an early freeze out, and you will be left with a lot of dark matter in the universe. On the other hand, if you have a large cross section, you will have a late freeze out, and you will have too little dark matter. So basically, you can use this simplistic scenario to kind of constrain what is the cross section that you expect from this very simple new particle. And that's what you get. You get actually, when you compare the cross section with the observed cold dark matter, or the density of dark matter that we observe, we see that we need a cross section which is almost exactly 3 to 10 to minus 26. This is a very important value because, this is basically of the same order of magnitude of the cross section of the electroweak interactions. So if we assume that this particle here, the way this particle interacts with the standard model is actually through the weak interaction, by basically assuming a new particle in this regime of GeV to TeV, which is also the weak scale mass, we need a cross section on the weak interaction strength to actually explain the observed relic density. And that's what we call the WIMP miracle, because it's a very simple assumption that we have a new particle that doesn't interact with the light, interacts only through to standard model through weak force. And this particle, if it has the right mass and the right interaction on the weak scale, we actually get the relic density. So that's impressive. That's why we call this the WIMP miracle. Now, this is a very important number, and that's actually normally the number that we will try to probe always with experiments and things like that. Now, sorry. What are the possible dark matter particles that we can have? So basically, the WIMP particles, they are between GeV and TeV, hundreds of TeV. There is also an upper limit on this mass that comes from unitarity, from the fact that the probability of quantum interactions has to be smaller than 1. In the thermal bath, this actually puts a very constraining limit on hundreds of TeVs. Now, of course, this is just a question of perspective, because we do have, and we have been having over the last decades, lots of different types of candidates that can actually explain dark matter in different ways. You can actually explain the relic density through other mechanisms, not only the freeze-out mechanism. You can actually explain through lots of different mechanisms, and that will actually have different dark matter particles that can explain that. Even new particles in the low mass regime that we call, or high mass particles, or even primordial black holes, and that you will actually have 10 to 66 electron volts. So that's actually, if you put in electron volts here, you actually get something to 10 to 66 or something like that. So you actually have about 90 orders of magnitude of all the different masses of particles that can actually explain dark matter. And there are lots of beyond standard model theories that predict the existence of either WIMPs or new particles that can actually explain. So what we can do now is that we can look for these particles. We can try to find signs of these particles. And there are several ways of doing so. So here is my dark matter particle that will interact through some new physics that I don't want to define right now with the standard model particles, right? We have different ways of that this interaction can happen. We can either have what we call indirect interaction, and then we can probe through indirect searches. This is basically what I just mentioned in the beginning, annihilation of dark matter particles into standard model particles. But we can also have processes such as scattering of dark matter particle with standard model. If you have dark matter particles flying through the universe, they are also flying through here. So you can actually build a detector underground to avoid cosmic rays, to avoid any kind of thermal fluctuations. You can cool it close to zero, and then you can wait for a dark matter to scatter on your liquid, on your cool liquid, and you can detect this. This is what we call direct searches. There are lots of experiments that do that currently. And finally, we can also bang these standard model particles together on the other direction, and we can expect to create dark matter. And that is also done in the LHC, in accelerators. This is also done, and this is detected by what we call missing transverse energy. If you know the energy that came into the collision, and you have less energy that was actually expelled after the collision, you have something that is missing. And if it's missing something that you couldn't detect, if you couldn't detect, it's perhaps dark matter. So that's the basic idea. I will be focusing only on this, on the indirect searches, okay? And the main idea of this type of searches is that if you have dark matter in the universe or in the galaxy, that it's annihilating somewhere in the galaxy, this will produce these final states that can be either stable particles or charged particles. If these are charged particles, this will be what we call charged cosmic rays. They will, after the annihilation, they will propagate through the galaxy diffusively because you have magnetic fields, and they will arrive, they will lose directionality, and they will arrive on Earth from all directions. But we can still study these using spectral signatures of the cosmic ray spectrum that arrives on Earth. Then we can also have final states which are neutral, gamma rays or neutrinos. They are not deviated from their trajectory. They point directly to the source, so we can actually do these studies using both spectral signatures and spatial signatures of the emission. Now let me talk to you about searches with gamma rays. That's one of the neutral messengers that we have in this type of indirect searches. Now, again, I'm not going to go through all this. You already had 3 lectures on this. So basically, I'll be talking about all these high-energy gamma rays, such as Fermi-LET, and high-energy, very high-energy gamma rays, which are either imaging atmospheric Cherenkov or air shower particles. Now, you already saw this, that the gamma ray will interact with the atmosphere. So you either put a detector above the atmosphere, such as Fermi-LET, or you put a detector in high altitude to detect the particles in the shower, or you put something closer to the ground to detect the Cherenkov light on the ground. Okay, these are the 3 different types of detectors that you can have. Now, a Fermi, you also already saw that. This is a satellite 1 square meter box that detects gamma rays using pair conversion. Now, the IACT world, you have Veritas in the north, MAGIC also in the north, and HESS in the south. Now, we have the future of IACTs, the Cherenkov Telescope Array. I hope that you also heard a lot about CTA, that it's started its construction. It's expected to have 2 arrays in the north, in La Palma, and in the south here in Chile. and we expect to have a factor of 10 better in flux sensitivity, larger energy coverage, field of view, twice better angular resolution and energy resolution. Now, it's a global effort of more than 1,300 scientists, 210 institutes, and more than 32 countries involved. There is a very strong Brazilian participation with lots of institutes here in Brazil participating in this in CTA, both in the initial science perspectives, design, construction, etc. In particular, let me draw your attention to that we also contribute to instrumentation of CTA here in Brazil. It's a 100% Brazilian project that actually built the support of the MST, of the middle-sized telescope camera. There was the whole project analysis, prototype, verification, reproject, and final product was all done here in Brazil, in the state of São Paulo, together with industry. There are 2 prototypes already constructed, delivered, and approved. And there was a patent that came from this development, and now we already have budget approved for the construction of 10 of these structures that will initially be built in the north and then in the south here in the next 2 years. Now let me go back to some other telescope detector that we are building, or we plan to build. That's the SWGO. Which is supposed to build a new detector here in South America, probably Chile, Peru, Argentina. We are still deciding where. In high altitude, in the Andes. The main idea is that we're going to cover a wide field of view and a wide energy range. There is a collaboration. Brazil is involved in this collaboration. Now it has more than 50 partner institutes in 14 countries. And the idea is to actually have a project, an idea to what exactly to be built by this year or next year. We will have this idea. So there is a lot of participation there as well. Now, there was a paper back in 2019 where we actually made some estimates on the we produced some what we call strawman design for SWGO. It's basically a blow-up version of Hawk with much more detectors and much larger. And then we actually can use these instrumental response functions to derive limits to whatever science you want to do. Now, the main idea of indirect detection through gamma rays is that if you have a self-annihilation rate, the self-annihilation rate will be proportional to the cross-section of annihilation to the density squared and inversely proportional to the mass of the dark matter particle mass. Of the particle. Now, this will annihilate through what we call primary channels. Normally, we assume 100% annihilation into one primary channel. That's a way that we do experimentally. After this, these are very heavy particles. They will hadronize or decay, and they will produce stable final states. And here, of course, we are interested in the gamma rays. Now, if we want to convert this rate into a flux, we have to introduce the energy distribution, right, which is basically this spectrum here, and we have to integrate over the line of sight the density. Now, this energy distribution is what we call the spectrum, the gamma ray spectrum. It will typically be a continuum with a cutoff at the energy equivalent to the mass of the particle, because you can't produce gamma rays with an energy higher than the mass of the particle. And we might have, in some cases, these features close to the dark matter particle mass, which are lines or bumps. And these are very interesting features because they are smoking gun features in a spectrum that if you detect a line at the GeV-TeV range, there's no other way of explaining this other than the decay or annihilation of a heavy particle. That's it. Now, the other thing that you have to do is to integrate the density square over the line of sight. Let me see how much. And for that, you have to have a description of how the density of dark matter is distributed over the line of sight, or basically how it is distributed in the targets that you're looking for, so in these halos, right? So you need to model the halos of the galaxies that you have. Now, these come either from numerical simulations of galaxies. Nowadays, you have very advanced cosmological simulations of galaxy formation and things like that. Normally, these predict a very cuspy profile or a density that grows towards the center. Here you have several different models. Typically, we separate them into this Caspian chord. The chord profile, they basically come from the observation of certain galaxies. We actually don't see typically this cusp towards the center. In a lot of galaxies, you don't see them. You actually favor a constant density of dark matter towards the center of these galaxies. That's what we call these chord profiles. These are analytical functions, and normally what you do, or what astronomers do, is that they fit these profiles they use the traces of the dynamics of the galaxies, like velocity dispersion of stars or globular clusters and things like that, that trace the gravitational potential, and you inject these density of dark matter to try to fit these distributions, and actually you derive the parameters that are left there. These are examples of the Milky Way, of the halos that fit the Milky Way velocity distribution of stars and globular clusters. We are here at 8.5 kiloparsecs, and this is the difference that we get from different profiles. So there's a huge discrepancy. And if we convert into what we call the J factor, that integral of the square density of dark matter, you actually get discrepancies in the very inner parts, which are several orders of magnitude. So what we normally do is that if we want to predict some signal, we actually have to assume several different types of models, or we take two extreme models, so we have a bracket on what is the predicted signal that we have. Now, we can have additional contributions to these annihilations. They can either come from astrophysics. For example, galaxies, when they form, they don't form only one halo. You actually have several sub-halos that are formed. And since the flux depends on the square of the density, these small halos will actually contribute quite a lot to the flux. And these are actually very true for globular clusters. For galaxy clusters, for example, we can have what we call these boost factors of the signal, using substructures which can go up to a factor of 100. We can also have some propagation effects like inverse Compton, when you have electrons or charged particles in the final state. You can also have adiabatic growth of the dark matter cusp around black holes, supermassive black holes or intermediate mass black holes. These additional contributions can also come from particle physics. There is this one example, is the Sommerfeld effect. It's an effect of, it's very similar to the formation of these hydrogen energy states in quantum theory. But if you, instead of a Coulomb potential, you assume a Yukawa potential, which is weak interaction, you actually have this formation of these quasi-stable states before it annihilates. If the annihilation happens at very low velocity, you actually have these energies, or for certain masses, you actually have these cross sections which are much higher and much more probable to annihilate. We can also have these radiative corrections, which are basically, if you have charged particles also in the final state, you can have virtual internal Bremsstrahlung, you can have these final state radiation, radiative corrections on the spectrum, and you generate these lines. We can also have secondary radiation in the case where you produce charged particles in the final states. I already mentioned inverse Compton scattering, but we can also have Bremsstrahlung if the annihilation happens in an environment with a lot of gas. You can also have Bremsstrahlung emission. And if the annihilation happens in a magnetic field region, you can also have synchrotron radiation that is emitted. So all these can contribute to the final flux of dark matter annihilation. Now, we have several targets where we can look for dark matter. We have the galactic center, which has the advantage of being very close to us. So it has a very high concentration of dark matter. We have this problem of not knowing if it's a cuspy profile or a chord profile. And we also have a lot of non-thermal emitters also in the galactic center. So it's a very tricky region to look for dark matter, but it's supposedly the place where we expect the highest flux of annihilation of dark matter in the galaxy, in the universe even for us. We have dwarf galaxies. They are located within 100 kiloparsecs from us normally. They're extremely dark matter dominated environments. They're actually one of the only environments where we know that we have at least a factor of 10 or 100 or even 1,000 times more non-luminous or dark matter than visible matter. And they also have this advantage of not having any non-thermal emission. They don't produce gamma rays by themselves. There's no high energy phenomena happening there. So if you detect a gamma ray coming from a dwarf galaxy, that's also another possible smoking gun for dark matter annihilation. Then we have galaxy clusters. They also have a very high dark matter annihilation luminosity predicted. They have this thing of having a lot of substructures. Each galaxy basically is a substructure of the biggest halo. But in some clusters, you have to be careful because they also have astrophysical non-thermal emission. And then we can also look for local galaxies on our local group. And one of the examples is the Andromeda galaxy. They are also relatively close to us. And in this case, we can also constrain with secondary radiation that I just mentioned to you. Let me start by telling you, or going, let me go here. It's complicated. Yeah. Now, I will start by telling you a little bit about some recent results that we have on dwarf galaxies. Now, they are, like I mentioned, they are the most dark matter dominated system in the universe. So we have several of these. There are satellites of the Milky Way. Here are some photos of these dwarf galaxies. There are several dwarf galaxies which are what we call typical dwarf spheroidal galaxies. We can actually constrain the dark matter halo of this galaxy quite precisely because we have measurements of stars and the velocity dispersion of stars, and you can actually measure the dark matter density towards the center. So it's one of the places where you actually have a measurement of the halo. It's different from the Milky Way where you don't have the measurement. In the case of the galaxy center, because the gravitational potential of the galactic center in the center is dominated by the stars of the bulge, not by dark matter. But since dwarf galaxies are dominated by dark matter, when you measure the gravitational potential, you are actually measuring dark matter there. So that's why they are so interesting for us. Now, there are several what we call classical dwarf galaxies. They are known for the past decades. And in the past decade or so, we actually had a large number of surveys that actually increased the number of dwarf galaxies that we observed in the Milky Way. For example, the Dark Energy Survey actually has this coverage here, and we discovered several dwarf galaxies in the south galactic plane. And very recently, a lot of the gamma ray observatories, Fermilet, HAWK, Veritas, MAGIC, and HESS, they actually joined forces with all the dwarf galaxies that they had observed. Fermilet, both Fermilet and HAWK, they observe the whole sky, or Fermilet observes the whole sky, HAWK observes the whole northern hemisphere, but the other IACTs, they actually pointed instruments, so they only see the galaxies that they point to, so they don't see all the galaxies, but they joined efforts. None of them observed any gamma rays coming from dwarf galaxies. So if you don't observe gamma rays, what you can do, you can constrain the possible parameters of dark matter that would give you a signal. So what you do is that you have this joint likelihood analysis where you have a null hypothesis, which is no signal, and you try to find what is the pair of these two parameters, especially sigma v, the cross section, and the dark matter particle mass, that would give you a signal at 2 sigma or 3 sigma or something, and you can provide an exclusion limit. So how do these exclusion limits look like? They look like this. Normally, we put in a plane of annihilation cross section here versus the dark matter particle mass. We mention what is the channel, so that's the primary channel, so we assume 100% annihilation into this bottom quark and anti-bottom quark. This is not very realistic from the theoretical point of view. If you have a theory, a full theory, when you calculate the branching ratios, you're going to have, I don't know, 50% into quarks, 20% into leptons, etc., etc. But for us, since we are providing experimental limits, what we like to do these modeling dependent limits, so that's why we assume 100% into one channel. If a theoretist wants to test his theory, it just needs to rescale the limits with the right branching ratios that they have in their theory. So what we limit here is everything that is above these lines, okay? So this is the limit of the combined limit. So let me tell you what are each of these lines. So these are all the instruments, okay? Fermi-LAT, Hawk, Hess, Magic, Veritas, all the combined limits of each individual instruments. And then in black, you combine all of them. So you can see that basically Fermi in this case dominates a lot of the limits, at least for below 10 TeV, and then the rest is IACTs. And again, we exclude everything that is above this line. So if the cross-section would be above this line, we will have detected with more than 95 confidence level. Now, for this study, it was tested 3 different channels: BB bar, W plus, W minus, tau plus, tau minus, or a quark, a boson and a lepton, and then we use J factors, the measurement of the galaxy's density distribution from a specific paper. And these are the limits for the 3 channels. So the combined upper limits can go up to 3 times the individual limits. And what we can see here is that below basically 2 to 30 TeV, depending on the channel, the limits are largely dominated by Fermi-LAT. Then above 2 to 30 TeV, depending on the channel here, IACTs and Hawk take over. And that's basically the bottom line of these limits. Okay, so thermorelic cross-section can be tested by Fermi for every energy or every mass below a few hundreds of GeV. So basically, the thermorelic cross-section was already tested and excluded by Fermi-LAT. Actually, this is an old result. We know this since 2015, that they exclude something below roughly 100 GeV using dwarf galaxies. Now, the good thing of dwarf galaxies is that there are new observatories, surveys that are observing the whole galaxy. For example, these recent deep surveys, they have observed 33 new ultra-faint dwarf galaxies. There's a new generation of surveys, such as the Rubin Observatory, and the Rubin Observatory is actually predicted to observe all the dwarf galaxies up to the virial radius of the Milky Way. So we expect that in the next decades, we're going to know all the dwarf galaxies, and we can use this legacy data from Fermi-LAT or Hawk or these large field of view observatories to actually constrain and look back to see if we see gamma rays from these dwarf galaxies using these observatories. So this is a projection of the limits that we expect from Fermi. This is only for Fermi. If we have, instead of 15, we have 60 dwarf galaxies in 15 years of observation, you actually start to push this line towards higher masses. So that's how normally these limits go. Now, let me tell you a little bit about the galactic center. Now, the galactic center has been observed by IACTs. In particular, it has been observed by Hess. Hess is the only IACT in the southern hemisphere, so it's the only one with a constant observation of the galactic center over sky, so with very low zenith angle. And it has been conducting a deep, very high energy survey of the galactic center, and which covers a very large area around the galactic center, up to 5 to 6 degrees. If you take just the 2014-2020, you have more than 500 hours of observation. And we can use that to see if we can detect any gamma rays coming from annihilation of dark matter. So that's what was done. So one of the first things that we do is that we cut off this inner part here, because we know that there are gamma rays coming from there, and it's a very complex region. So this serves as a very difficult background, so we basically ignore it and we try to see if we can see gamma rays coming from this halo area. So we slice into small bins and small rings around the galactic center, and we use this 2D likelihood analysis using both spectral and spatial information about the signal to derive the limits. So we assume, just for the sake of comparison with other experiments, typically we assume the same halo for everyone if we want to compare the limits. We assume that A Nasto, this is a peaked profile. It's less peaked than the Navarro-Franken-White, which is also very typical. So it has the advantage that it has the dependency of the Navarro-Franken-White. And close to the center, you don't continue with the density that grows towards the center. You actually have a density that becomes a little bit flatter. Now, these are the limits that we get with HAZ. These are the most constraining limits nowadays, up to date, in these channels, in the TV mass range. So you can see that for both the W plus, W minus, and tau plus, tau minus, we can actually reach limits below the relic density. So you can, the other way of seeing it is that we exclude these dark matter particle masses that would have the thermal relic density around 1 TeV here. So we also did a estimate for the future observatories. We did an estimate on what CTA would observe, what SWGO would observe. CTA is a slightly smaller field of view of 1 degree around the galaxy. And for SWGO, we assumed a 10 degrees, so it's a large, wide field survey. Again, we excluded this region. We did the same game as for HAZ. We did the rings, concentric rings around the galactic center, and we derived our limits. So this is what it looks like for tau plus, tau minus. In blue, you have Fermi, the prediction for the projection, also Fermi. The red one is for CTA, the gray one is for SWGO, thermal relic, and this is for HAZ. So basically, again, we exclude everything that is above this line, and we managed to, what we show is that with these future observatories, we will actually be able to constrain all masses below 100 TeV, below the thermal relic value. That's the case for this channel, tau plus, tau minus. In the case of W plus, W minus in BB bar, we go a little bit lower. Instead of 100, we go to 80. Instead of 100, we go to 30 TeV. But again, we constrain everything, a lot of particles, models below the thermal relic, below the TeV range. So that's what we expect. The advantage of these type of complementarities between instruments is that we can actually use both to detect a signal. In case we detect a signal, for example, here is the flux sensitivity of CTA. This is the flux sensitivity of SWGO, and you can see that they are complementary, whereas CTA can be sensitive to a spectrum of dark matter. This is for the different masses of dark matter. At the TeV, SWGO would be sensible to the flux at the tens of TeV. So you can actually confirm, in case CTA observes a gamma ray, confirm the cutoff, for example, and confirm that it's a dark matter signal. We can also have decay sensitivity. So instead, the only thing that changes here is that instead of a rate that depends on the cross-section and the density squared, you have a rate that depends on the density, and you depend on the lifetime of the particle. It's one particle, it decays with a specific lifetime. And instead of what we call J factor, we have this D factor. Now, we also estimated these D factors here. Again, here, instead of constraining everything that is above, we constrain everything that is below this line. And for SWGO, for example, we show that a wide field observatory actually is able to constrain and give limits which are extremely sensitive. Now, let me tell you a little bit about local group of galaxies, in particular about the Andromeda Galaxy. And I want to tell you about this result because it's one of the most constraining that we have currently. It's a very recent result. It comes from the observation of the Large Magellanic Cloud, which is very close to Earth, around 50 kiloparsecs from the Earth. And it was observed by this Australian Square Kilometre Array Pathfinder, ASCAP, which is a radio telescope. And the observations are part of this survey here called EMU, Evolutionary Map of the Universe, that has been published. Now, they use this data to actually constrain the potential dark matter annihilation signal in case of secondary emission. So basically, if you have charged particles in your final state, electrons or positrons, you can actually, because the Large Magellanic Cloud has some magnetic field, you can produce synchrotron. This synchrotron can be observed with this telescope. And they actually they managed to have very strong limits. They basically, if these are to be believed, because this depends on the magnetic field, okay? So there is a dependency on the magnetic field of the limits, but they actually managed to constrain everything below basically 1 TeV for masses, for particles annihilating to BB bar, if I'm not mistaken. Now, I will not go into detail on the what we call galactic center GeV excess, but let me just summarize for you in case you are interested on this topic. This is an emission that has been detected in the galactic center by the Fermi-LAT. Initial claims were done by Goodenough and Dan Hooper back in 2009. There was a lot of controversial discussion in the community for more than 6 years, and finally in 2015, the existence of this excess finally got the blessing of the Fermi collaboration, and everyone was wondering, is it a dark matter signal? So there is a residual signal that looks a lot like dark matter. Now, again, I'm not going to describe this whole topic. It would be a whole presentation, but let me just use this slide that was adapted from a slide by Christopher Venegar that shows basically all the papers that have mentioned or tried to analyze the same data and that claim that, okay, this excess is likely dark matter, or didn't have any claim, or in black that it's not dark matter, and some people that even claim that excess is not even there. So you can see that over the time, it started with a lot of green, a lot of people questioning the green, and basically since 2016, a lot of people saying that, okay, it's not dark matter, it's probably pulsars. I'm going to mention a little bit. But recently in 2019, there was a rebirth of the claim that it's dark matter because they were questioning some of these analyses that were done before. But even today, there are also people that claim that it's not dark matter. We are just not modeling the galactic center very well. But if you're interested, there's a lot of papers there. You can check it out. Now, there's also a lot of detectors that are coming, gamma ray observatories, CTA, gamma 14, SWGO. There's a lot of very interesting experimental efforts that are coming in the next decades. Now, what about neutrinos? Let me mention neutrinos a little bit. Neutrinos, basically, the study on indirect detection of dark matter with neutrinos follow the same logic of gamma rays. Basically, you have annihilation. Instead of gamma rays, you look at the final state neutrinos. So here, if you notice, I just changed the gamma to a nu. Okay? Now, we have lots of detectors that are coming. For example, KM3net, June, Antares, IceCube. So the game is the same. Here are the current limits by Antares and IceCube. Here, 3 years, Antares in red. Here, compared to Hess and Fermi. So Antares is the best limits that we have in TeV, but it's not yet competitive to Hess and the other limits. But KM3net actually can actually probe really close to the thermal relic cross-section in the TeV range, so we have to wait for KM3net to come and constrain dark matter. On the other hand, for decaying dark matter, because these detectors can see a lot of the sky, they can actually constrain the decaying of dark matter through the universe, and IceCube is actually the best limit that we have for dark matter particles above the hundreds of TeV and PeV. It's actually a very powerful detector for that. Now, there is another very interesting detection mechanism that we can do with neutrinos, which is trying to detect dark matter in the sun. So if you have dark matter that is flying everywhere, it can be captured by the gravitational potential of the sun, and dark matter will annihilate, self-annihilate in the center of the sun. Now, most of the subproducts of annihilation will not escape the sun, but that's not the case for neutrinos. The neutrinos can actually escape. There is also another type of mechanism that can escape the sun. This is a very specific model where you have not only dark matter, but also a dark mediator. And if you have a dark matter that annihilates into the mediator, and the mediator later decays, then this mediator can actually escape the sun, and then you can have a standard model. But this is a very specific model, but it's also very interesting. But in the case of neutrinos, you have an equation that gives the amount of neutrinos that will annihilate and how many will escape the sun. This is P survival is the escape probability. And this escape, this annihilation rate will actually be proportional to the capture rate. And the capture rate will be proportional to the cross-section or the scattering cross-section. And that's a parameter that we look with direct detection when you have dark matter that it scatters. So it's not annihilation cross-section anymore, it's scattering cross-section. And both Antares and IceCube actually looked at the sun, and they actually put very constraining limits. Notice that here the scale and the units changed. Pico is a direct detector, so you actually can see that these type of searches are comparable to direct detectors of dark matter. Now, let me finish by mentioning briefly cosmic rays, because I think I'm on my time already. Let me see. 10 minutes, so, okay. Then I have enough time. I can go not so fast. So for charged cosmic rays, like I mentioned before, the main difficulty is that you're going to have particles that will propagate through the galaxy. And this propagation is actually quite complicated. Here is one example of all the different terms that you can have on your propagation through the galaxy. You can have the diffusion term, you have your source spectrum, you can have energy losses that you heard about in Brian's lectures. You can have convective winds, spallation, cosmic rays, if they are massive, they can disintegrate into less massive cosmic rays, etc. So it's actually quite complicated, but luckily we have a lot of Monte Carlo simulations that do that. We have a lot of codes, Gauprop, Dragon. There are lots of these codes that actually do that for us, and you can actually compare the spectral signatures that we detect on Earth with these predictions. Now, this is a very simple model. For example, this is normally what we do. We make simplistic assumptions about the galaxy. We assume that the galaxy has a thin disk and then a thick disk, and all the propagation actually happens in the disk. Then you have all these different reactions. You assume some cylindrical symmetry, etc. And you can also define what is the most relevant process and all. So you can simplify these things. If you're interested, there's this very good review from 2012 from Lavalle and Salati. It's actually very interesting. Now, there is one detector that detects cosmic rays in the GeV range currently. That's the AMS. AMS is a detector on the International Space Station. It's basically this box here on the International Space Station. And the advantage of AMS is that it has so many layers and detectors that you can actually discriminate what is the particle that entered the detector. So either an electron, a positron, a nuclei, etc. So what we have in the annihilation of dark matter is basically the same formula, okay? It's the cross-section, the spectrum, and the density of dark matter in the whole galaxy. So you have annihilation in the whole galaxy that generates cosmic rays that comes to us. And we can, for example, plot what is the expected fraction of positrons that we expect on Earth, or what is the expected antiproton fraction that we expect on Earth from the annihilation of dark matter. So I'm mentioning about fractions here, antiproton and positron, for a very specific reason, is because AMS actually detected an anomaly on the positron fraction and antiproton fraction. This is for proton and antiproton. You can see that the observed here by AMS is much higher than what we expect from what we call secondary production of the galaxy. This is a known excess, from 2015, they published this. But this excess actually is only so large because at the time they published that, we didn't know so much about the propagation in the galaxy itself. And ironically, it was AMS itself that gave a lot more data to understand better the propagation in the galaxy, that when you put the new information about the propagation in the galaxy, these limits, this excess is not actually that high. So this is basically what you have in terms of uncertainty of the propagation, solar modulation, etc. But there is still some uncertainty. We still have a little bit of excess, but in case we assume that we don't have excess, we can actually do the opposite game. We can put constraints on dark matter that would produce an excess. So again, here that's what was done back in 2017. This is the type of limits that AMS can put. Here again, for a specific channel, they can actually constrain the thermal relic cross-section for around the hundreds of GeV, similar to Fermi-LET. Now, the positron, there was also an anomaly detected in the positron fraction above 10 GeV. And the main thing is that from propagation physics, this ratio was never expected to rise. Okay, it was expected to go down. Now, the problem is that if you try to interpret as dark matter, it's actually quite tricky, because the particle model that you have to assume, basically the first thing is that it's a particle that only annihilates into lepton. That's what we call a leptophilic dark matter. These are very exotic, even within the field of dark matter, which is already exotic. A leptophilic dark matter particle is even more exotic. They would have to be very massive around the TeV. And the problem is that at TeV, the cross-section that you will need is something much above the relic density. So this is a big problem. Basically because this is already excluded. If we take, for example, these limits from Fermi-LET, using dwarfs, and even the AMS antiproton, we already exclude basically the interpretation that the positron excess is coming from dark matter. So yeah, dark matter interpretation is possible. Actually, AMS themselves put all the time in their presentations that dark matter could explain this excess, but it's already in a lot of tension with observed gamma ray experiments, for example. Now, what are the other possible explanations of this positron excess? And basically, pulsars. Pulsars are sources that can produce electrons and positrons in equal amount. So you basically will produce positrons with a 0.5 positron fraction. And if you have this coming from pulsars, you will actually increase the positron fraction, because if you notice the positron fraction here, you see like it's just, the rise is from 5% to 10%. So if you have a 50% positron fraction that is coming, it may increase this fraction to this, right? Now, so here is, for example, a prediction of the pulsars. If we assume a specific model of all Milky Way pulsars, this is the AMS points, you can actually explain these quite well. Now, there is a question about whether the spectrum has the right cutoff. So the whole AMS discussion relies only on the final points, and we expect the AMS will actually give some new results next year, and they claim that it will give the definite answer whether it's dark matter or not, 2024. The last time they said anything was in 2016, and ever since they've been radio silent, as far as I know. So I know that next year that we expect some results from them. There is a lot of cosmic ray telescopes that are coming, that are currently being constructed. There's DUMPIT, there's LHASO that is already constructed. We have very high energy detectors. So I didn't mention these, okay? So I didn't have time to mention LHASO. LHASO has a very recent dark matter publication. Auger also has a very recent dark matter publication last year. And finally, another thing which is very interesting that I also didn't have time to mention is this dark matter in extreme astrophysical environments. I give you just the archive. This is a white paper for one of these decadal surveys in the US, where they described all the different topics that you can have. For example, stellar evolution, how dark matter affects it, binary mergers, how axions affect it, how you super heat neutron stars and pulsars with dark matter in the environment. So there's a lot of interesting stuff there. I didn't have time to talk about it, but if you're interested, please have a look. And that's it. Thank you.
Thank you, Alon. Questions?
Hey, thanks for the talk. I hope my question makes any sense. Correct me if I'm wrong, but I think at the beginning of the talk you said that we have observational evidence to believe that, to think that dark matter could be a particle, could be a strong hypothesis. I mean, we have extensions to the standard model to explain the thing if we assume that is a particle, but do we have observational evidence to think that is a particle?
We have indirect evidences that it's a particle, and that comes mostly from cosmology, right? Like if you assume in the standard lambda CDM cosmology, you have this soup of particles, and you can actually study what is the relic density of all the particles that you have in the universe: hydrogen, helium, neutrinos, etc. And this density, and the density of dark matter of a non-baryonic matter in the universe is observed. We observe with the power spectrum of the CMB. That's observed. So if you want to explain that power spectrum using the lambda CDM model, the one very simple way is to assume that you have a new particle in the thermal bath in the beginning of the universe, and then you explain that. Without that new particle, without the dark matter particle, you can't explain the power spectrum of the CMB. So it's basically that thing that I showed right in the beginning here. Did I show? Yeah, this I didn't. This thing here. This is the power spectrum of the CMB, right? Like you look at the fluctuations of the CMB, you see what is the scales which are most predominant there, which are so basically you have a scale of 1 degree, then you have a scale of, 50 degrees or whatever, and you see that certain scales in the universe, when the universe was 300,000 years, some scales are more predominant. So it means that those structures were, the most part of the structures had exactly that time at that time. The only way to produce that, if you don't assume any new particle in the thermal bath, that it's a cold dark matter particle, that it's in there, you can't explain this. It's as simple as that. Yeah. Yes, exactly. Yeah, so anyway, we need a mass, we need a particle to be interaction there with the thermal bath. Like that's the lambda CDM model. You need particles. Everything we know are particles, at least under the current paradigm of particle physics. We have particles everywhere, so we need to assume that in the lambda CDM in the beginning of the universe. Or fields, if you want. Like fields.
Yeah. That was what I wanted to complement. It may be a field.
Yeah.
A classical field in certain regimes behave like matter. So there is absolutely no contradiction in assuming that there is a very light field which is actually oscillating, and during the universe evolution, this oscillation produces something that behaves precisely as matter. It's absolutely indistinguishable from a particle. So it's a possibility. Okay. So just to complement
Right,
what
right.
Ion was saying.
Further questions, comments? To complete the number of steps my watch requests per day, I have to go up and down once more. So I need one more question to go up and down here. I knew the joke would get one more question.
Just someone up there.
So thank you for a nice talk. When they study neutrinos that are produced, as a secondary decays from thermal annihilations or decays, are those neutrinos studied like standard model neutrinos, or do they consider maybe oscillations into standard neutrinos that could also be, part of the dark sector, or new standard, non-standard interactions, or
Right. Yeah, here I limited myself to this model independent tests, right? But yeah, you can have tests which are model dependent. You can assume what is your dark matter particle, what is the nature of this particle. It can be actually sterile neutrinos is one possible candidate for dark matter itself. So it can be a sterile neutrino. Now it will behave in practice phenomenologically, it will behave exactly the same. It will annihilate, it can annihilate. Now sterile neutrinos, they are a little bit different in their cosmology. They will not have this freeze out mechanism, they will have a freeze in mechanism. It's a little bit different. But then you can have after you can also have annihilation into, you can have order, you can have a whole, actually this whole field of particle dark matter, you can have a whole lot of dark sector particles. They can annihilate into dark sector particles but neutrinos, yeah, oscillation, you have the same process that you have for any standard non-thermal production of neutrinos, right? You produce neutrinos, they can oscillate, but what we want is to detect with a telescope, a neutrino telescope. So in that sense, it doesn't matter so much if it's a muon neutrino or electron neutrino. You want to detect just the energy of the neutrino through the Cherenkov light, right? So.
Any other question? Now I'm running the risk to have cramps here.
Hi. Can you go to that slide that you showed all the orders of magnitude for the masses?
Right.
Yeah.
This one.
Yeah, that one. Because, I mean, I know we measured that there's something missing.
Right.
So that should be dark matter. There's also dark energy that you didn't even comment. That's another stuff.
Yeah.
But I don't know, I get the feeling that we don't know enough for the theories to be more directed. Because for now, cause I don't work with dark matter, I work cosmic rays. And for me, it's like it can be anything. As long as it matches the little measurement that we have, it could be anything. And it goes from too many orders of magnitude in mass. So I think my question to you would be, what sort of measurement would you think that we need so we could constrain that better? Not just assuming that it is a particle, but assuming that it could be other sort of stuff.
Right. You're right in the sense that it can be a lot of things. It can't be anything. It needs to be something massive because we see gravitational effects of it. This is undeniable and unavoidable. The fact that the universe, that our theories, that has a huge anomaly in the universe, which is the missing mass of the universe in all scales of the universe, you can't deny that, or you can't run away from that, okay? So you need to explain it, and with something that is transparent to light. So it has to be massive, and it can't interact with light. After that, yes, you do have a lot of possibilities. Now, I just showed you, actually, throughout all these indirect detections, one of the very interesting aspects of this type of searches is actually if we detect a spectrum if we detect a signal and we can characterize the spectrum, then we can actually say a lot about this particle, right? Because you can say about the mass, you can say where, because if you detect the cutoff, say you detect right, if you detect a flux that has a cutoff at the TV range, a very sharp cutoff, or a line, again, if you detect a line, that's a smoking gun for a massive particle that is decaying or annihilating. There's no other mechanism that can produce a line at TV, no other physical mechanism that can do that. So if you can detect some kind of cutoff, very sharp cutoff or something, you can actually identify the particle, right? Once you detect some particle, then you can construct accelerators exactly, perhaps some linear accelerator at exactly that energy to try to see some resonance. I don't know. Then you can go on from that to try to identify this new particle. That's exactly what we do with all the particles that we discovered in the past with accelerators and things like that. Right, so it can be a lot of things, yes. I think that's why the experimental efforts are so important now, because it's only through them that we're going to start to exclude all these theories. But I don't know, the theoretical efforts are interesting. Mathematically, they are interesting. Sometimes they can give you some interesting ideas on how to look for new particles, new specific type of particles. You can also have specific experiments to look for certain specific dark matter particles, such as, for example, axions. I didn't mention axions, but it's one type of particle that can be a dark matter candidate, and there are very specific phenomenology that are related to axions. Because they can convert into photons, so you can actually look for them with magnets and things like that. So it's actually quite interesting. So yeah.
Further questions, comments?
Thank you for your lecture. Mine is a comment. So in CERN, there's been implemented a massive horoscope taking advantage of the high luminosity of the LHC. And the idea is that most of these beyond standard models share this characteristic that these particles, these weird particles, have long lives. And so taking advantage of these and not putting a detector, let's say, around the collision and way above, you can detect these strange signals. So just a comment that.
So what is the idea? You have the beam.
Yes.
And inside the beam, you're going to have something.
No, way above, hundreds of meters above the collision point. Oh. It's the project's called Methuselah. Okay. It's a massive horoscope, and so it's focused on LLPs, long-lived particles that will decay from Higgs exotic decays.
Okay.
And yes, and one of them would be candidates for dark matter.
Okay.